Hi, I'm Howard, and today I'm going to be showing you the SweetMaker MotionSensor library, which is a library to help you use motion sensing in your projects. Motion sensing is great fun, it adds richness to your projects. Check out this one which I uploaded to the project hub. It's as a hat which, as you move, the lights change colour. But using motion sensors can be complicated. There is complexity which is in there, which you may not be clear when you start out, but as you get going you often stumble over it. The motion sensor library helps to take away some of that complexity and helps to show you how to use motion sensors. It uses the MPU 6050 motion sensor, that's what's under the hood, and it, like other sensors, gives you a rotational quaternion as its output. These can be more robust representations of orientation than Euler axis or yaw pitch roll. We're not going to look in detail at quaternions, but it may be helpful as background to understand that a rotational quaternion is different to an orientation quaternion, and again as background, knowing what a rotational quaternion looks like can be helpful, and how you use it to create an orientation quaternion. You can go and look at Wikipedia to understand that better. But for now, we're going to jump straight into the tutorial, which is an example of the motion sensor library. We're going to be using this today. So we start by instantiating a motion sensor instance. And then in setup we initialize that, and that downloads code to the MPU 6050. It sets it all up, and we're ready to go. As part of the SweetMaker framework, when there's a new sensor reading, we get an event which our event handler captures. Within the main loop, we're simply updating the SweetMaker framework, and those events will then get auto-generated. But we're also looking for some input from the serial input, which we're using just to help run through the tutorial and just to orientate you. That's all that we've got in here. Check serial input, and depending on what number we put in, we'll just go into a different run mode. And in each run mode, we are simply outputting different values, starting with the raw rotational quaternion values. So we're going to dive straight in and have a look at that. I'm going to open the serial plotter. The motion sensor is going to be starting up, and one thing I didn't show you, we have the motion sensor set up here for our use. Tell it to go to run mode 1, and this is now outputting the raw quaternion values. And as I move this, those values change. The raw values aren't very intuitive to use themselves, and so we're not going to be spending any time looking at those in particular. But there is one thing which I need to show you. This is showing the current rotation. So if it's static, we expect these values to be static. But watch what happens when I move this and then stop moving it. We see that the values carry on moving for a while, and that is because the MPU 6050 needs to be calibrated, and we have code within the motion sensor library to allow that calibration. It runs a self-calibration routine and gives us calibration values, which you can use again at initialization. So we're going to go ahead and run that calibration now. While it's calibrating, the motion sensor should be level, pointing upwards and absolutely still. It takes about 10 seconds, so that should be nearly done. Just a couple of seconds more. And then once it's done, we should see now that the quaternion readings are robust and stable. When I stop moving, they stop moving. Bum, 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 bum. Perfect. We now have a calibrated motion sensor. So the next thing we're going to look at is your pitch roll angles. These are a more intuitive way of looking at the orientation and can be created from the rotational quaternion. These do use trigonometric functions, and so they are computationally more expensive to create than most of the other things, most of the other uses of the orientation which I make. Let's take a look. Your pitch roll, so as we pitch forwards and backwards, we see the pitch changing. As we move left and right, we see the yaw changing, and as we tilt to one side and back, we see the roll changing. So that's easier to understand. The library provides scales the output values to 16,384, the 14-bit value, 15 bits if you include the sine. Another thing to understand is that the MPU 6050 motion sensor has 6 degrees of freedom. It does not have a magnetometer, which means it does not know where north is, and its yaw is of an arbitrary rotation, and it will drift over time. So that means the yaw is problematic to use in your projects if you're trying to use some absolute value there. But the pitch and roll are good. Okay, so the next thing we're going to look at is gravity. So the MPU 6050, while it doesn't have a magnetometer, its understanding of gravity is robust, and so the gravity can be calculated, and it gives a very robust readings for gravity, and so those can be used in your projects. This is my go-to starting point if I want to understand orientation, is gravity. Also, it can be calculated very quickly and easily without any trigonometric functions, so the length of time to calculate it is minimal. Tilt X and Y we've looked at as that pitch and roll, but sometimes it's adequate rather than using finding that the pitch and roll angles. Sometimes we can simply make do with the sine of the angles, and that does not require the use of trigonometric functions, and so can be computationally preferable. Let's just take a quick look at those. Let me just make sure I know. Okay, number 5, that's the magic number I need to put in. So this is showing us tilt forward and backwards, and tilt side to side. Using the sine, and that is computationally more easy, quicker to create, and so that can be used if that's adequate for your usage. Okay. We can also use the MPU 6050 for finding out the rotational speed within 3D space. The motion sensor library produces a rotational quaternion delta, the difference between the last couple of readings, and by looking at the rotational angle we get an idea of the rotational speed. So we'll take a quick look at that. Now the values we get are actually very small. That's because the time difference between readings is small, and it's actually giving us the cosine of that angle, which changes even less. But if you get a quicker motion, you can see the readings do smooth out a bit. And when it's not mounted on a tripod, you can sometimes get some quicker rotation as well. This is often enough for you to make some use of in your projects, but where perhaps quaternions become more useful is in working out the how close the orientation of the sensor is to a particular direction you may be interested in. We're looking at how the z-axis, how closely the z-axis is to pointing in towards different directions of interest. So how close we are to pointing towards the z-axis, how close we are to pointing forward to the right and forward to the left. So we're going to be looking at those. So I've defined these orientation quaternions of interest, and we then take the dot product between it and gravity, and that gives us a cosine of the angle between those two. So as it becomes closer, that should get closer, converge on the value of 1 or 16384, because that's how we've scaled it. And as we get closer to one or the other, we will see those values changing accordingly. Okay, so we start by pointing towards the z-axis, and so our z-axis reading is close to 16384, and the forward right and forward left are both languishing down here. But as we tilt forwards, we see that change, and then as we tilt to forward and to the right, we see that the red one becomes dominant. And then, this is a little bit harder, if I tilt to the left, we find the green becomes dominant. And so this allows you to, in your project, be able to have different axes of interest and generate events when you start to point in different directions, which is great. When you start actually using one of these projects in the wild, you may come across an issue. You may find that the motion sensor isn't actually deployed level, or if you've tried to deploy it level, it may not be completely level. And it's helpful to provide a rotational offset to compensate for that. And the motion sensor allows us to do just that. It has an auto level function and provides and adds a offset. So let's put this back in gravity, looking at gravity mode. So this is as normal when it's level. The z-axis is large and x and y is small, that's pointing up. We apply an offset here, so let's say it was mounted there. Now let us auto level about that value. So we've auto leveled, so x and y are now 0 and z is large, and if we tilt forwards we see just the x value going up and down, and if we tilt to the side see the y value changing. So we have auto leveled it to be flat, but if we return to the picture of the hat, auto leveling sometimes isn't enough. Sometimes there's also a rotation about the vertical z-axis, which the motion sensor cannot auto detect. So we need to tell it about that. We actually explicitly need to tell it what the required rotation about the z-axis is. So we've got code here to tell it about a 45-degree rotation about the z-axis. So we are going to do that. So if we put in a 45-degree, well, let's just start there first, and let us undo the auto leveling, look at gravity and tilt forwards and backwards. We can see that just the x changes. But of course if this were rotated 45 degrees and we were to do that, then x and y would change together. But if we now auto level with a 45-degree z-axis in it, and now that's working as we want. So we tilt forwards and backwards, and only X is changing. Let me put that back in. You can see the X value on the key there. Also, if we were to put some tilt in there and auto level again, it can cope with that as well. So you can have your sensor with arbitrary orientations, and you can auto level about, and it will all work just fine. That is the SweetMaker MotionSensor library. It's designed to take the heavy lifting out of using the sensor in the real world, and to provide you an API for various different to detect various different events or values, such as the rotational speed, the tilt left, tilt right, how close it is to a particular vector of interest. I hope it's useful to you. Please let me know what you think of it, and come back and check out other projects which I plan to do in the future. Thank you and goodbye.